Good day and welcome to today's introduction to artificial intelligence. So I will try and record introduction to artificial intelligence today, regression, some aggregation algorithms, then we talk about classification, then probably tomorrow I'll talk about the unsupervised part of things. So let's go straight into it. So artificial intelligence. Artificial intelligence is a science of making things smart, can be defined as human intelligence executed by machine. So a broad term getting computers to perform human tasks. The scope of AI is disputed and constantly changing over time. Let's go deeper. So basically, artificial intelligence is giving computers the ability to actually do what humans do, like how we think and the likes like that. So where are we at? The system implemented today are a form of narrow AI, a system that can just do one or a few different things as well or better than human, like recognizing objects, gesture. We train it to learn. So basically what we are saying here, that AI is still narrow, that is narrow AI. It simply means, of course, humans, for example, you can drive, you can cook, you can eat, you can walk, and a lot of things like that. But then the AI we have in recent time, the AI we have today, is how they can do one thing better or like humans, or maybe two or three things like or better than humans. So we are still narrow with AI until we get to that place where we can say an artificial intelligent machine can do what humans can do. We can't really necessarily say that artificial intelligence has gotten to that point yet. So AI common use cases, so object recognition, speech recognition, sound detection, natural language processing, sentiment analysis, creative, prediction, translation, restoration and transformation, and the likes like that. So basically what we are saying here is we can use AI for all these different things. So you can always dig deeper and learn some of these things that you can use AI for. So machine learning. So what's machine? Machine learning can be defined generally as an approach to achieve artificial intelligence through systems that can learn from experience to find pattern in a set of data. So basically what we are saying here is machine learning is an approach to artificial intelligence. There are other approaches. So basically what machine learning does is you learn from data, that is you learn from experience, from already done events to do future events, to learn the pattern of things. So for example, you can have a machine learning algorithm that does for example house price prediction, an algorithm that predicts what's going to happen next, a stock exchange market and the likes like that. So we have then we can use it for other things too. We can use it for voice recognition, because it learns from people's voice. It's able to say, okay, this so person's voice. Then we have speech recognition, that is being able to say, oh, this is what this person is saying at this particular time. Then translation, that is being able to translate from one language to another. So that's that. So learning by example. So machine learning also is all about predicting stuff, essentially it's intelligence, because it takes some data, that is it then learns pattern, that is it takes data, that is for example voices that we've had in the past, it takes them, then learn the pattern in the voice, that's that, then classify new data in data it has not seen before. That is, for example, you've learned, okay, this is my voice, this is your voice, this is your mom's voice, this is your dad's voice. Then machine learning learns the pattern in each voice and say, okay, this is now so person's voice. So by the time you give it new data, it's able to say, oh, this is so person's voice and not this person's voice. So that's that. Then the beauty of machine learning is that it learns by itself from data passed to it. You know, unlike when we're learning Python program, we have to say if statement, that is, if this is this, do this, if this is this, do this, if this is this, do this. But then in machine learning, it learns from data itself and is able to predict. For example, imagine you want to predict whose voice is whose voice. It's going to take a very long time, because you have to say, okay, when the voice is deep, then that's my dad's voice. When it's a bit light, then that's my voice. When it's lighter, that's my mom's. Then when it's even lighter, that's my sister's, and the likes like that. It's going to be too cumbersome to actually analyze. But then machine learning can easily learn from data and be able to predict what's going on. So the different ways of doing things. So write a computer program that explicitly to, then computer program that learns from example. So this is what Python programming normally would do for you. That's traditional programming. Then machine learning will learn from data and be able to classify the data. So that's that. Then we have deep learning. Deep learning from here on we can define generally as a technique of implementing machine learning. On such deep learning technique is a concept known as deep neural network, that is, yes, which you may have heard of. If not, no worries, all will be explained. Essentially, deep learning is in the context of DNN, is where code structure can write and arrange in layers that loosely mimic the human brain, learning patterns of patterns. So basically what we are saying here is deep learning is essentially we having a neural network, like this, the way our brain works. You can't really explain. In fact, the medical science has not been able to explain how the human brain works. So deep learning essentially is a way of actually modeling algorithms the way human brain works. So sometimes we call it black box because we can't necessarily explain how the neural network works, but then you can build patterns on patterns, so patterns on patterns, so it can learn on so many neural networks. So that's what deep learning essentially is. So summary, these concepts go back quite some time. The idea of AI goes back to 1950s. In the 1980s, machine learning became to grow popular. Around 2010, deep learning drive large progress towards achieving narrow AI system. You can see how three terms are linked, subset of each other. Essentially, deep learning drives machine learning, which then ultimately can enable artificial intelligence. So basically, what we are saying here is, okay, in the 50s, we have some deep learning, the machine learning algorithm that were already modeled, but then the computing power available then was not enough to run these algorithms. Same in the 80s, but in the 2010s we already started having GPUs for playing games, so we're able to use that for machine learning. For example, my current system is around 16 gig RAM. Then I'm using like NVIDIA GeForce RTX, that's around 4 gig dedicated. So you can imagine the first computer I used was a Pentium system. So you can imagine how much deep learning I'll be able to do with my Pentium system compared to this. Now imagine what computers they were using in the 80s. So that's what actually drove deep learning to come to the limelight. So we can actually use our regular systems today to run machine learning. But then you can always go back to the cloud and use probably Google GPU, or you use Amazon cloud, or you use Azure cloud, that's the Microsoft cloud. So you can use any of these things to drive your machine learning algorithms. But then your normal local system cannot run the normal machine learning algorithm that we are going to use during this course. But then if you can't, you can always try, I've forgotten the name of that, I'll put in the comment section, that you can use on the cloud. That's by Google. I've forgotten. It's a Google Colab. Yes, you can easily use Google Colab in case your system cannot run the algorithms we will be running. So moving on from there. So we have the inspirations here. So here is feature attributes. So we have feature aka attribute features aka attributes are used to train an ML, that is a machine learning system, that are the properties of the things that we are trying to learn. So you can see, you can check for the weight, you can check for the color, you can see the texture and the likes like that. For example, orange is from apple. That's why, for example, essentially that was why they had to beat off a part of the Apple logo so that we can be able to recognize, oh, this is an apple, not an orange. For example, imagine having this in black and white. It almost looks like Apple logo without the beating off part. So that's that. So then features and attributes. So taking fruit as an example, features of a fruit might be weight, color. Two features would mean that there are two dimensions. That's 2D systems. So 2D system may be plotted on a graph. Its features are represented in a numerical way. So that's something, this is essentially an example. In the plot in the right, ML system can learn to split data up with line separating apple from orange. This can now be used to make future classification when we plot new points on the system as that has not seen before. Yes, anything above the orange below is apple. So basically we have apple here, we have oranges here. So anything above this point is apple, anything below this point is orange. So that's that. So we have, okay, we have features and attributes. Choosing useful input features can have big impact on the quality of ML system. Some features may not be useful enough to separate data points. In this example, we take bad features of fruits, ripeness, and seed counts that do not allow us to learn any distinguishing factor of the fruit. It takes practice and thought to figure out what are the best features to use, as they are not always as clear as this trivial example. So basically, for example, apple has fruits. Yes, it has it has seeds. Then what's it called now? Orange too has seeds. So we are using the seed count or how ripe the apple is and how ripe the orange is to predict. Then we are going to make a lot of mistakes, because then apple is a ripe apple, a ripe orange, the seed count of apple, a seed count of orange, we can't really distinguish them. But then if we use the color that we used here essentially before, we can always do that. So non-trivial data too here. So non-trivial data, our fruit example uses 2 dimensions. If you needed 3 dimensions to separate the data meaningfully, we can split the plot in a 3D chart and separate the clusters of points with a plane that divides the 2 set of data as shown. Note, most ML problems have even higher dimension, like 20D or even millions in the case of image recognition. Each pixel is a feature, whilst we find it hard to visualize anything higher than 3 dimension. Computers and ML can. The principles are the same. So basically what we are essentially saying here is, because it's very difficult for us to plot more than 3D, but then computers can plot up to 20D. Just we can't really visualize it on our 2D plane, but then ML models can learn from all those dimensions of plots. Actually, humans too can do that, but then we can't really plot them out on our 2D screens. That's essentially what this part is telling us. A note on dimensions. So adding more dimension can often help separate out the data points, allowing the ML system to split data up into groups for classification as shown on the right. So that's what we are doing here. So too many dimensions, however, can lead to overfitting, which means it knows the example data perfectly, but if you give it something new it has not seen before, it won't be able to generalize well enough to get new things correct. Okay, what we are saying here is essentially is, when you give it too many dimensions, it does what we call overfitting. What we mean by overfitting is, when when we were in school, there was something we call cramming and there's something we call understanding. So when we do ML that understands, that's when we don't overfit. But when we do ML that crams, that's what we call overfitting. That is, it crams the data points that we have, so it's able to say, okay, this is this by just the examples that are available to it. But then when you bring a new one, when they bring a new problem, you might not be able to solve it. That's same thing with our ML model. When it overfits, it cannot necessarily generalize to the new problem that you are giving it. There's another problem we call underfitting actually, but then let me check the next slide. Maybe we have that. So data hunting. Once you know features to use, big challenge is finding enough unbiased training data for all those features in a format that can be fed into an ML system to learn from, depending on the type of ML algorithm being used. Imagine you want to recognize cats. You may need 10,000 example image of cats if you want a chance to get decent results. Data is not always images. Could be table of data with multiple features, text sensors, recording, sound sample, more depending what it is you want to do. So basically what we are saying here is, hunting for data is an essential part of machine learning problems. For example, let's say you want to do text recognition, then you need a lot of text, like corpus of text that you need to work on. For example, the example we used here, we want to recognize cats, we need over 10,000 images of cats. Then we need over 10,000 images of not cats, so we will be able to make a decent comparison. So that's essentially what we are doing here. So an ML system cannot predict stuff it does not know about. So basically what we are saying here is, if an ML system has not learned something, it cannot predict what it has not learned. So that's essentially what we are saying here. So okay, I guess this is where we'll stop on introduction to ML. Then the next video I'll do regression algorithm. So we'll start coding. So we have different types of machine learning algorithms. We have the supervised, the unsupervised learning, and the likes like that. So here I will explain what we mean by supervised learning. So we have 3 types of machine learning. We have supervised learning, unsupervised learning and reinforcement learning. So here is supervised learning. Supervised learning, where ML program is provided with training data that are labeled. You tell the system how to categorize the exam. For example, color, weight label, red, that's for color we have red, orange and green. For weight we have 20 gram, 30 gram and 150 gram. Then for label we have apple, orange, apple. So given the input, color and weight, I am telling the system what what the expected output label is in each case. So orange or apple, that's supervision. The ML system must then use the data to predict the future unseen input. Currently, this is the most studied area. So what I'm saying essentially is you have label data. That is, you've given the each of the out you've given the computer the output that you will be expecting from it. So for example, you can't have this algorithm now and then it will predict for you, like let's say melon or watermelon. It will be a lie. Like there's no labeling of watermelon or anything here. So the only possible outcomes here are just apple and orange. So and the input that we are using is red and color and weight. So essentially what we are saying is we've labeled data. So supervised learning actually has two aspects. We have the regression, we have the classification. What we mean by regression is where the output is continuous. For example, when you're talking about price of houses, or you're talking about weight, or you're talking about things that are continuous, that is things that can be counted, these things that can be measured, that are greater than each other in measurement. Then we have another one that we call classification. Classification is essentially what we have here. Classification is when you can group them into maybe 2 or 3 groups. So you can say, okay, there is group A, there is group B. Then you can't necessarily say group A is greater than group B. For example, you can't necessarily say apple is greater than orange. I can't necessarily say orange greater than apple. So something like that. When you can only have them in classes, you can necessarily say, okay, they are greater than each other, or they can be measured. Like this one is bigger, this one is better, something like that. So that's what we mean by unsupervised learning. Then we have the unsupervised learning algorithm. So the system must learn from unlabeled data sets. Imagine you have a bunch of points in a graph representing 3 things. Machine learning must realize by itself there are 3 distinct clusters and categorize them as such. This is tricky as the number of clusters may not be known in advance. So it can take a best guess. Also, sometimes the clusters are not as clear as the ones shown here. So basically what we are saying here is, for example, let's say you want to cluster the people in Ibadan, for example. How do you classify people in Ibadan? How do you classify them? Are you going to use their education? Are you going to use where they live? Are you going to use where they work? Are you going to use their income? Are you going to use the type of house they live in? Are you going to use their community? Are you going to use the number of children they have? And things like that. Then how many classes do we want them to be in? Because there is no labeling of people in Ibadan. You can only say, okay, these ones and these ones. We can't necessarily say, okay, this one is better than this one because this one earns more than this person, or this person lives in this area than this area, or this thing like that. So basically we can only use best guess and give our algorithm. Okay, for example, here it's obvious that we have 3 clusters here, but in Ibadan, for example, you can't necessarily say there are 2 clusters, or there are 3 clusters, or there are 4 clusters, or even in Nigeria. So something like that, we have to use our intuition. Then over time we'll be able to say, okay, this is what to do and this is how to go about things. Then we have reinforcement learning. Reinforcement learning, this is learning by trial and error through reward and punishment. The program learns by playing the game millions of times. The reward system, when it makes a good move, this strengthens the connections to make moves like it did. Then when it loses, we give it no reward or negative reward. Over time, it learns to maximize reward without human explicitly telling it the rules. It can learn to be better than human performance when it finds place that no one even thought of doing before. So basically what we are saying here essentially is our algorithm learns, when it comes to reinforcement learning, learns by trial and error, that is learns by doing. For example, let's say, learning how to drive, you can't really essentially, okay, give the algorithm, okay, this is how to drive. There's no way to say that, but then you can put a sensor in your car, then it learns from you, like, okay, when this happens, not a sensor, actually sensors, because you need cameras, we need either radar sensors or the normal camera sensors. We need sensor that can sense depth. We need things that can recognize objects. So when it sees an animal on the way, it stops. When it sees human on the way, it stops. Then we need things that can recognize bombs from actually things that are used to block the road, things like that. So it is able to sense all that. Then it's able to know, okay, when I see red light, I have to stop. When the policeman is pointing his hand, is showing it hand at me, I have to stop. Things like that. Then it needs to be able to recognize speed limits for each environment that it finds itself. So things like that. So that's reinforcement learning. Then, for example, if you have played chess on your phone, you played against your computer, that's reinforcement learning. So it learns by example, it learns by doing. Then here is ping pong game here too. The computer learns from the example. Then here is X and O game. The computer learns from playing over time. It can play against itself. Unlike we humans that we can't really play against ourselves, we can play against itself over and over again. Then there is the reward system, like that is for it to know, okay, when it's doing the right thing, we reward it. When it's doing the wrong thing, we punish it by collecting the rewards it already got. So by so doing, it wants the reward, we program it to want the reward and do not want the punishment. So by so doing, it learns better, and sometimes even learns better than human. For example, the Go game, the algorithm learned the Go game and it was able to beat the world champion of Go some years back. That was, I think, 5 or 6 years ago, and that's actually a very good leap for machine learning. So inspiration, many ways. There are many ways in which machine learning system can try and learn patterns to classify data presented to it. We shall go through some very simple examples. Real machine learning system often use more than 2 dimensions on the next few slides to give you some ideas, insight of what is going on behind the scene. These examples are chosen to help aid understanding. In reality, for cutting edge research, there's much more going on, sometimes even combining multiple methods or more complex concepts beyond the scope of this deck. But the basic principle of finding patterns through some mathematical methods still apply. So basically what we are saying here is we have some examples here. So remember the high school when you add plots x and y axis graph, then draw a line of best fit. This is like the simple machine learning system. In this example, what the line you draw, you can predict, with the line you draw, you can predict x, which with value of y given probably be given even if unseen example is extended the line further. So what we are saying here is essentially this regression. That is, if you have this line of best fit, then if you are given the value of x, you can predict y. If you are given the value of y, you can predict x. And here is another one. So that's that. Then here is another example. This one is for classification, or for clustering actually. So we have, here is a cluster, here is another cluster. Then we use this line. Then here is an outlier actually, because this one from the color it's supposed to be here. So we have outliers in our data. So sometimes we have outliers, then we find a way of fixing them. But that's why we say essentially machine learning algorithms are sometimes not 100% accurate. Actually, they are never 100% accurate, except you did something we call overfitting. And then overfitting will not be able to generalize to other data. So here is another clustering algorithm. That's here we use k nearest neighbor. So k nearest neighbor, don't worry, I will explain k nearest neighbor when we get to where we use k nearest neighbor. Then we will not necessarily touch neural networks. We can always keep on checking my YouTube channel. I will touch on neural networks in the future. Thank you very much, and don't forget to subscribe to this channel. Bye bye.